In the last class, we have seen applications of laminar flow. We have used Navier-Stokes equations and solved them for various situations. Although simplified, but various situations, they resulted in one-dimensional or one first order or second order ordinary differential equations. That's why we could have an analytical solution. What we are going to do now is to try look at more of non-Newtonian fluids. So that's the topic for discussion in this lecture. We are going to start with just a recap of where we are. This is where we are. We are on topic number 6, and related to microscopic balances, we are going to look at non-Newtonian fluids now. Just to quickly revise what we have done in the last class, what do we mean by no slip and free slip boundary conditions? What is a symmetry condition? A related question to that is, wherever velocity is maximum, is it the same as symmetry condition or it is not the same as symmetry condition? Think about that. Velocity can be maximum when we have, let's say we had talked about flow of a liquid film along the plate. That time velocity was maximum at the edge of the film, at the interface between the film and the air. The velocity was maximum. Gradient, was it 0? Think about other situations when we talked about two coaxial cylinders. Inside was a rod and rod was being pulled. Where was velocity maximum? Did the maximum velocity mean that velocity gradient is 0? Think about those. Okay, so that's what we have to think a little bit more detail about what this symmetry condition means. Recall all the steps that you require to get to the velocity field for a given geometry. So think about all these aspects. Try to quickly recap all the problems that we did in the last class, and that will help you to get started in this lecture. So what we saw last time is that the stress versus strain behavior was linear. These are called as Newtonian fluids. Right? So whenever strain is 0, stress is 0, and then the slope of that stress versus strain line is the viscosity of the fluid. We call that as a viscosity, dynamic viscosity if you like. And most of the fluids that you will normally come across, air, water, dilute aqueous solutions, light organics, means benzene, toluene, xylene, of that type, they will all, acetone, methanol, simple solvents, they will all be a Newtonian. Look at this graph. Sometimes the stress versus strain graph is linear, but it has an intercept. The intercept is called as is denoted as tau naught. It is called as yield stress. The reason it is called as yield stress is, look at this. If the stress value is even anywhere below tau naught, there is no strain. There is no strain means there is no deformation. There is no deformation means there is no flow. So unless and until the stress exceeds this value tau naught, therefore it is called as a yield stress. Liquids do not flow, or that those kinds of fluids do not flow. Only liquids will exhibit such a behavior. Examples of that would be toothpaste, ketchup, things like that. Very thick slurries, they don't flow even if you just hold them down. So even if you take the toothpaste, open the cap, hold it upside down, it will not flow unless you squeeze, unless you apply more stress, unless you overcome this yield stress. And then beyond yield stress, we can write an equation of a straight line. So stress would be tau naught plus mu times strain, and then mu is the viscosity slope, but that viscosity is only defined beyond this yield stress. Below the yield stress, the stress versus strain behavior is just a vertical line. The stress versus strain behavior is just a vertical line. Right? Slope is infinity, viscosity is infinity. Right? Beyond this tau naught, only then we define a viscosity. Till that time, liquid is not deforming, right? No flow. Sometimes, look at this third graph. Sometimes the stress versus strain behavior is non-linear. It passes through origin, not like this Bingham plastic, it passes through the origin, but the slope changes. In this particular case, slope is reducing. In this case, slope is reducing. Okay? That means at this point, the viscosity is given by this slope. At this point, viscosity is given by this slope. That means viscosity is reducing with the strain. So if you plot viscosity for this particular case, if you plot viscosity mu versus the strain, and remember strain we are denoting by a letter gamma, viscosity will reduce as you increase the strain. These are called as pseudoplastic fluids, and typically many polymeric solutions behave like this. Carboxymethyl cellulose is something that you will use in your experiments. Look at the fourth graph. The stress versus strain graph is non-linear like the pseudoplastic, but look at the curvature. At this point, let's say we are looking at this particular point. Let's highlight that. Yeah, let's say we are looking at this particular point. Slope is this much. That means this is the value of viscosity slope. At this point, slope is higher, viscosity is higher. That means viscosity increases with the strain. So if I plot that, if I plot mu versus gamma on the x-axis, mu on the y-axis, viscosity will increase with gamma. These are called as dilatant fluids, quicksand. And the example that you saw in the video, I will again come back to that. That was a dilatant fluid, how it allowed people to walk on that liquid. Sometimes your stress versus strain behavior could have a yield stress as well as it could have a curvature like this, right? So then the equation would be tau naught plus it will be some equation that will describe this. Now what equation describes this kind of behavior? That behavior is called as Ostwald-de model. It is simplified. It is in simple language, it is called as a power law model, which means we are saying that stress tau or tau yx, if you want to be very precise, it's a good idea to be very precise. Tau yx is some constant k multiplied by dvx by dy raised to n. So k is called as this consistency index and n is called as power law index. Now look at what happens if n is equal to 1. So if n is equal to 1, it is a linear behavior, straight line. It's a Newtonian fluid. So n is equal to 1 means Newtonian fluid. That means viscosity would simply be equal to k. That's for Newtonian fluid. If n is less than 1, then the behavior would be something like this, a pseudoplastic behavior. And if n is more than 1, the behavior would be like a dilatant fluid. So n is more than 1, it's called as a dilatant. N is less than 1, it's called as a pseudoplastic. And in either case, any one of these cases, you can say, you can separate this out as k dvx by dy raised to n multiplied by n minus 1 multiplied by dvx by dy. So k dvx by dy raised to n minus 1 we can define as an apparent viscosity. Apparent viscosity. Okay, so this would be, it is an apparent viscosity. Viscosity is not constant, it is an apparent viscosity. Apparent viscosity is reducing with the strain rate. Apparent viscosity is increasing with the strain rate, right? So that's what is the meaning of apparent viscosity. Okay, let's go forward. So just like this power law model, there are other models as well that describe this behavior of stress versus strain. One of them is called as Ellis model, given by this expression, or a cross model. Look at this cross model. Cross model has a viscosity behavior like this. If you plot mu versus gamma, so at very low values of gamma, what will happen? This is mu raised to So this gamma raised to n, so 0 raised to n, so it's like almost like 1, 0, sorry, 0 raised to any number, it is 0, so this is 1. So then mu infinity will cancel out, mu 0 would be the value, so that's value is called as mu 0. It is called as zero shear viscosity. This would be mu 0. And as you increase the value of gamma, this denominator becomes larger and larger value. This whole term tends to become 0. Mu becomes equal to mu infinity, infinite shear viscosity. So this is mu infinity. So mu value changes between mu 0, zero shear viscosity, and mu infinity, infinite shear viscosity. The behavior is something like this. It asymptotically approaches this mu infinity. It asymptotically approaches this mu 0. Okay? That's how the viscosity variation is for this particular model. There are other models like this which also describe this behavior. They are called as Karau model. Right? Again, these are very commonly used for different polymer solutions. The reason why these different polymer solutions behave in this non-linear manner is that, remember, when we derived this for using kinetic theory of gases, we said that molecules are point masses, the distance between them is large, mean free path, and they collide only when they go to the only when they travel the mean free path. So molecular size is very small. There are no molecular interactions. On the other hand, when you take polymeric solutions, these polymers are long chains and these chains are entangled. And when they are entangled and when you deform, these chains will pull away from each other or slide over one another, or sometimes one of the chain may pull another chain, may prevent it from deforming. Okay? That's what gives rise to this non-linear behavior. That's why it gives rise to non-Newtonian nature of the fluid. So many polymeric solutions will behave in a non-Newtonian manner, and many slurries. So slurries means solid particles in a liquid medium. If the concentration of the solids is very high, like toothpaste or ketchup, solid strength or solid concentration is very high, it behaves like a semi-solid. There's only very little liquid, there is lots of solids. So these solids don't slide over each other very easily. They have rough edges, so they kind of slide and sort of entangle or stop each other. A lot more friction is required to get a particular deformation. That's what gives rise to this yield stress. That's what this gives rise to these non-linear behavior, dilatant behavior. Okay. Blood, you can imagine that blood is a containing water and lots of dissolved salts. It dissolves salts, dissolved proteins. There are cells, blood cells, white blood cells, red blood cells, and so on. So lots of solids are present, and blood tends to behave like this yield stress, fluid. It has a yield stress, although that yield stress is very small. Okay, but blood behaves like this Bingham plastic fluid. Okay, just to give you some examples now, just to show you what some of these mean. So there is a beaker, it is open to atmosphere from the top, there is a tube at the bottom, and this is a Bingham plastic fluid. Now we see what happens. So beyond a certain weight only it flows, beyond a certain stress. Let's go forward. So what it means is that the Bingham plastic fluid, unless I overcome the yield stress, that's this video is showing you the meaning of yield stress. Here's another video. Look at this video. So if you come back to it later, what will happen is this ball will spread like a fluid. If you have a drop of, if you spill some liquid, how it flows and covers the whole surface. So after some time, this ball will cover the surface. It will spread like a fluid. That's why it is called as a fluid. Now this fluid behaves differently with different shear. How long you experience it, how long you allow the shear to be exerted on that fluid. So when this fluid is kept on the surface, the weight and therefore stress is acting on this fluid for a long time, and the viscosity reduces with time, and therefore the fluid or the ball spreads. Whereas when you bounce it, the impact or the stress on that ball is only for a very short time, and viscosity is very high for a short time, and therefore it bounces back, behaves like a solid. So viscosity behavior depends on how long the shear is applied. So fluids where viscosity depends on how long the shear or how long the force is applied, these are either called as thixotropic or rheopectic fluids. Let's go forward.
Speaker instead. I can even cut it to length.
See the fun part?
This is especially the case with large molecules. This
See fun part? He's trying to pour the liquid and is bringing it back. Well, he's trying to pour the liquid
is especially the
and
case
he's trying to
when
bring
you
it
are
back.
dealing with materials that I can pour into this beaker. No, I think I'll use this beaker instead.
And now once it is being poured, it can be
I can
cut,
even cut it to length.
liquid can be cut like a solid. Right, let's go back. Let's go back. Liquid can be cut like a solid. See that? These are called as viscoelastic
No, I
fluids.
think I'll use this beaker instead.
These are called as viscoelastic fluids. They behave like an elastic material.
I can even cut it to length.
Let's go forward. We had seen this, people walking on this liquid. Now that is a dilatant kind of fluid. You can see it has so much solid content. It's as if like a paste it is falling. It is not falling like a liquid. It is falling like it is like a paste. And when this person is walking rapidly, the strain is very rapid on the surface, and therefore the viscosity is very high, and therefore the person doesn't sink. But if a person walks gently, strain is very low, like that small boy, you remember in the first video, a small boy actually sank inside the pool. So strain is less, and if strain is less, viscosity is less, people can sink in that. So this is a dilatant fluid. You remember the videos related to siphon, tubeless siphon, that this syringe is getting filled even when the tip of the syringe is outside the liquid, as if the liquid is getting pulling itself up automatically and going through this opening and into the syringe. This is again because of viscoelastic behavior, as if there is a elasticity which is making this liquid rebound and go into the syringe. viscoelastic fluids. The Weisenberg effect, rod climbing effect. You see the rod and you don't get a vortex, you get a rod climbing effect. Again, this is because of the viscoelastic nature of the fluid. So fluids have very dramatic properties which can give you, which if you don't understand properly, can give you a lot of trouble when you start designing plants and things, equipment and so on and so forth. Okay, so here is a problem. Now we have a flow of a non-Newtonian fluid in a pipe. So imagine this is a pipe, very similar problem to what we did in the very first problem when we did applying Navier-Stokes equations. But now we are going to say that it is a non-Newtonian fluid, right? So recall all the 7 steps. First step, coordinate system. This particular case, cylindrical coordinate system. Our axis, this is our z axis. R is away from the axis. Recall that is our R, and theta is around the axis. Okay, cylindrical coordinate system. In which direction is the flow occurring? Z direction. So we better take equation of motion in the Z direction. But now we are not going to take Navier-Stokes equation. We are going to take equation of motion in terms of the stress terms. In terms of the stress terms, we are not writing in terms of viscosity terms because it is a non-Newtonian fluid. Okay, so use properly appendix B5. That gives you the equation of motion in terms of stress terms. Okay, use that. Now simplify. Let's simplify. Steady state. No VR, no V theta. Equation of continuity tells you del Vz by del Z is 0. Tau theta Z is not there. Why? Because flow is symmetric. Tau ZZ is not there. Why? Because dVz by dz is non-zero. Flow is fully developed in the sense that whatever happens at any location, any Z location, same thing happens at any other Z. This is called as fully developed. So only these 2 terms remain. So simplify this now. Think about what boundary conditions you are going to use. Simplify. Okay, so here is the solution. So you will have 0 left hand side minus dp by dz minus 1 by r del by del r of d by dr of r tau rz. Again, you can take it on this side, and minus dp by dz is delta p by l. Integrate once, you will get r tau rz is equal to delta p. So r is brought on this side. Integrate once, it will become r square by 2 plus c1. Now what condition we can use? At r is equal to 0, center of the pipe, r is equal to 0, center of the pipe. Symmetry means there is no stress. Symmetry means there is no stress. Vz is symmetric from all sides, right? Therefore the gradient, remember what we said in the Newtonian case, r dvz by dr is 0. Same way here, r tau rz is 0. So if r is equal to 0, r tau rz is 0, c1 is 0. C1 is 0. Second case, at r equal to r, Vz is 0, no slip condition. That is the same as earlier. So now if you integrate this, you will get that tau rz is delta pl r by 2. Now look at Birchfield-Lightfoot's book, appendix, the definitions of tau rz. Tau rz is mu dvz by dr. Now if it's a non-Newtonian fluid and it is described by the power law model, we can say that tau rz is k minus dvz by dr raised to n. Remember that minus sign in the Newton's law of viscosity, minus sign is really indicating the direction of how Vz is changing. If Vz is reducing as r goes up, then that negative sign is there, right? In this particular case, Vz is reducing, Vz is maximum at the center, Vz is 0 at the wall. Vz reduces as r increases, so that negative sign is there, and that negative sign is really for the velocity gradient, and therefore we are saying that the power law model is like k minus dvz by dr whole thing raised to n. Now we can substitute that. bring k here, take 1/nth root of both sides, put the minus sign there, and now we can integrate. And once we integrate, put this boundary condition at r equal to capital R, Vz is 0, and then you will get this profile. You will find that Vz is equal to this expression. Don't trust me, derive this expression for yourself. Just a way to make sure that you got the right answer. What can we do? How do I make sure that we have got the right answer? Right, if I put n is equal to 1 and k is equal to mu, I should get back the same expression that I had when we had talked about in the last class, laminar flow through a pipe of a Newtonian fluid. So if k is mu, this will become delta p by 2 mu L, n is 1, this vanishes, n by n plus 1, it will become 1 by 1 plus 2, so it will become delta p by 4 mu L, r square, 1 minus r by r square. So you get the same expression as we had earlier. So now find the flow rate, maximum velocity, average velocity, and friction factor versus Reynolds number relationship. It is just a matter of mathematics. You are just to go beyond this, do all the same steps as we had done earlier for the Newtonian fluid, laminar flow of a Newtonian fluid through a pipe. Pause the video. Only when you have got the answer, then only go forward in the video. Solve for yourself. Here's the answer. So V average would be delta P by 2KL, 1 by n, n upon 3n plus 1, r raised to n plus 1. Again, if you want to make sure that you have got the right answer, you have not made any error in the mathematics part in going from here to the average velocity, put k is equal to mu, n is equal to 1. You should get back the same answer that we had last time. We can rewrite this expression in terms of delta p on the left hand side and everything else on the right hand side, like the Hagen-Poiseuille equation, but now this is a Hagen-Poiseuille equation for a power law fluid. Okay. So delta p would be 2 raised to n plus 2, this expression 3n plus 1 by n raised to n, k l v average raised to n, d raised to n plus 1. If you put n is equal to 1, you will get the same as 32 mu L V average by d square, the Hagen-Poiseuille equation for Newtonian fluid. Right, so just check. Now friction factor we can get again as we can get it as easily. Friction factor, how do we get? Tau RZ expression we have. Right, tau RZ expression we have. Evaluate it at r equal to capital R, means wall of the pipe. Delta P R by 2L is tau W. Tau W divided by half rho V square is F. So you got now delta P D by 4L. Put this expression for delta P and you will get this expression for friction factor. Again, if you put n is equal to 1, you will get 16 by Ru. K will become mu. What we are going to say is, if this we are going to say has the same friction factor versus Reynolds number relationship, so we will say this is equal to 16 by Reynolds number, but on Reynolds number has to be modified. Reynolds number will be in terms of n and k now. Right? So then you can get this expression for the modified Reynolds number. That's how we define Reynolds number for a power law fluid. Okay? Get this for yourself. Do this for yourself. Let's go forward. Okay? Just to make you understand and just to make you feel comfortable with the numbers, we'll try to look at the typical values of stress and strain rate. Okay, so think about a pipe flow, laminar flow in a pipe. Okay, strain rate is given by 8V by D. Right? Recall, where do we get this from? Let's write that. Let's quickly write that. So our delta P laminar flow. Do I have it written somewhere? No, I don't have it written somewhere. Yeah, delta P, let me write that, is 32 mu V average, just writing V average L by d square. So I can bring the d here, this will go away, 1d I have brought here. I can bring the L here, this will go away, and I can bring 4 here, and then that will leave me 8 here. Okay. This 32 will go away. So what I will get, let me just rub that so that you are able to see it nicely and clearly. 1d has gone away, L has gone away to the left side. 32 out of the 32, 8, 4 we have taken here. So what we are left with is only 8, and mu of course was there. So 8 and mu I am going to write separately, 8 v by. Now this is tau w, and this is mu, and therefore this is gamma, 8 v average by d. Okay. So strain rate we can say is 8 v by d. So if I say velocity is 1.5 meters per second in the pipe, average of course, average velocity is 1.5 meters per second in the pipe. Whenever we say velocity, it is average now. Otherwise we will say that how velocity varies with z direction, or we could say v max or something like that. So whenever we just say velocity, it is meant as average velocity, right? Average A. If diameter is 2 inches, then 8 v by d strain rate would be 240 per second. That's how that magnitude, that's the typical magnitude of the strain rate in a pipe having this much velocity and this much diameter. If pressure gradient is 1000 Pascal per meter, stress would be delta P d by 4L, that would be 12.5 Pascal. That's the value of stress. So in your stress strain behavior, that's where we are. We are at a strain of 240, stress of 12.5. Strain of 240, stress of 12.5. Okay, let's go forward. Okay. What is the impact of this rheology? So imagine that there is a stirred tank. We are having a tank. We are agitating that with some agitator. We saw that we need a good agitation for making this fluid mix very properly. So one of the ways is to have an impeller. So wherever this impeller is rotating, we will have high velocities near the impeller, which means high strain near the impeller or high shear near the impeller. So I will have high shear. Let me just put this value, high strain, and correspondingly high gamma. And wherever we are far away from the from this agitator, liquid velocity has become very small, and correspondingly we will have low shear in these regions. Low shear, low gamma. Now if it's a power law fluid, what would that mean? Low gamma would mean, look at this, low gamma would mean high viscosity, and high gamma would mean low viscosity. So I might as well say that wherever in this impeller region we have low viscosity. In this region, wherever there is an agitator, we have low viscosity, and far away from the agitator we have high viscosity. So you see the problem now. We should not just say viscosity, we should just say apparent viscosity, because it is at that particular region, mu apparent. This is also mu apparent. Near the impeller, there is an apparent viscosity is low because the shear rate is high. So as if the impeller is rotating in a low viscosity liquid, it will nicely mix there, but far away the viscosities are large. Practically that region is not getting stirred. So what happens is we get a kind of a region in which only mixing is happening. Practically the outside region for all practical purposes is stagnant. It is behaving like a solid, hardly any viscosity, hardly any velocity, because the viscosity is very high there. Whereas near the impeller, it has a low viscosity, it behaves like a nicely mixed liquid. What we call this is that a cavern formation. Cavern, as if the cavern has formed, as if only the inside liquid is rotating, outside there is complete solidific, as if there is a complete solid, no mixing is happening. When you agitate food materials, chocolates and things like that, all these kinds of things happen. So you have to be very careful that you get a nice homogeneity when you mix high viscosity or non-Newtonian materials. One of the ways to calculate strain rate is to take it as some number related to tip speed or some number related to the rotation speed of the agitation. This has come from experiments. We are not going to go into details of that, but right now what we are saying is the strain rate is 14 times the speed of agitation. So if it is agitating at, let's say 2 rps, then the strain rate would be 28 second inverse. Look at this, 28 second inverse, and for a pipe flow it was 240 second inverse. So much higher strain rates in the pipe as compared to agitated tanks. Okay, can we go forward? Let's think about this. You can stop the video anytime, go back forth and make sure you understood all the concepts, then only go forward. Don't worry about these formulae just now. Okay, now here is some video. We will see this video, and I will talk as we go along. So there are two burettes. Left side is a Newtonian fluid, right side is a non-Newtonian fluid. Okay. Let's see what happens.
The levels are the same.
Levels are the same. Means if I apply Bernoulli equation, H2, if I say 1 is at location bottom, 2 is at the top, or take 1 at the top and 2 at the bottom, flow is from 1 to 2, it's easier to visualize that way. So H1 is the same, H2 is the same, the burettes are identical, same diameter, same length, liquid is filled to the same extent. Now the burettes are going to be opened and we are going to allow the liquid to drain. Question to you is, which liquid will drain faster? Which liquid will drain faster? That's a question to you. Okay, think about the answer, make your choice, whether Newtonian liquid will drain faster or a non-Newtonian, the right side liquid will drain faster. This is Newtonian, this is non-Newtonian. Left side is Newtonian, right side is non-Newtonian. Which will drain faster? Let's see. Valves are open at the same time. The bottom valve is opened at the same time.
Taking the same Newtonian fluid.
Yeah, this is the video, sorry.
One contains a Newtonian fluid, the other a non-Newtonian. The levels are the same.
Take your pick, which will drain faster. Oh, non-Newtonian is draining faster. Right side is draining faster.
The non-Newtonian fluid flows faster.
Take your pick. Non-Newtonian is draining faster.
However, after a while, it is overtaken by the Newtonian fluid.
Oh, now it is overtaken by a Newtonian fluid.
The basic phenomenon occurring here is more easily seen if the pressure head remains practically constant.
Reason? This is a pseudoplastic fluid. If it's a pseudoplastic fluid, let me just check another. Yeah, this is another video is there. Yeah, so if it's a pseudoplastic fluid, what happens? Pseudoplastic viscosity will reduce with shear. Now they are filled to the same height, there is a higher shear acting. So viscosity of a non-Newtonian liquid is lesser, it will drain faster. But as you go down, as the level drops, now the shear, or now the stress arising out of the hydrostatic head is less, viscosity is higher, it drains slower, and then Newtonian keeps on draining at the same rate. Therefore, it is overtaken, pseudoplastic fluid. So that's why the flow rates, how they depend on the pressure drop, on the stress that you apply, is you need to be very careful when you are transporting Newtonian fluid in a pipe versus a non-Newtonian fluid in the pipe. Here's another example. See the video and we'll talk as we go along.
Taking the same Newtonian fluid.
The fluid is the same.
Pressure head in one is twice that in the other.
Fluid is the same, Newtonian.
The ratio of rates of flow is also 2 to 1, as we expect from Poisson's law.
Height in the right side one is double, therefore flow rate is double. It's a Newtonian fluid. Now take the pseudoplastic material. Again, same material, fluid in both.
But if we charge both burettes with the fluid exhibiting nonlinear behavior
Pseudoplastic.
and apply the same ratio of pressure heads,
so pressure head is double.
Quite different.
Hydrostatic head in the right one is double of the left one.
With this polymer solution, when the head is doubled, the rate of flow is more than double.
Flow rate is more than double.
It appears that the viscosity is less at the higher velocity gradient.
Viscosity is less at higher velocity gradient.
This type of steady flow behavior is called pseudoplastic or shear thinning.
Another one.
There are some fluids
Dilated.
that create a contrary situation. For this suspension, the viscosity is higher at the higher rates of flow. This is called dilatant or shear thickening behavior.
So now the flow rate is less than double. Although the hydrostatic head is doubled, flow rate is less than double. So you might think I will increase pressure drop by a factor of 2, but you will not get a flow rate increase by a factor of 2. Okay. For shear thickening, dilatant means shear thickening, pseudoplastic means shear thinning. So in a pseudoplastic, if you double the pressure drop, you will get more than double the flow rate. Let's go forward. Okay, let's try to look at how do we measure all these viscosities. Now, if you look at in the laminar flow situations in the last lecture, everywhere, wherever we calculated the forces, we found that the force was proportional to viscosity. Force was proportional to viscosity, and the strain rate was there, right? Whether it is Couette flow, whether it is Poisson flow, whether it is between two cylinders, whether it is between coaxially moving cylinders, whether it is rotating cylinder, whether it is capillary viscometry, whether it is a capillary tube in which it is draining. So one of the ways in which we measure viscosity is called as a Couette flow viscometer. It is between two cylinders. So we did this as a last problem in the previous lecture. So there are two cylinders. One is the inner cylinder, other one is the outer cylinder. Outer cylinder is rotating, and we measure the torque on the inner cylinder. So if this gap is very small between the two cylinders, it's called as a Hacke viscometer or Brookfield viscometer. When the gap is small between the two cylinders, we can approximate it to like two flat plates, and the top flat plate is moving, right? Couette flow between two parallel plates. That's why we did that problem. And there you found that gamma is just delta V by delta R. You recall, go back to that lecture and calculate how we calculate the strain rate for two parallel plates. Right? And torque is proportional to the stress is proportional to torque divided by torque multiplied by the surface area, that is 2 pi I RIL. That will give you the force multiplied by Ri, that gives you the torque. So if I measure the torque, I know Ri, you can calculate the stress acting on this inner cylinder. We are measuring that stress, or we are measuring the torque required to keep it from rotating. So now we will get torque. We got gamma based on what is the speed of rotation, and we can now relate torque to in this manner. Torque or stress is equal to K gamma raised to N. So you can plot log tau versus log gamma. Slope will be N. You see slope of this line is N, log graph. It is 1000, 10,000, 100,000, 1, 10, 100, log scale, log scale. Okay, and then you will find that viscosity reduces with the shear. It's a pseudoplastic kind of fluid, shear thinning. Another one is a capillary viscometer. It's just like a laminar flow through a pipe, but it is a it is a very small tube, so that Reynolds number is definitely in the laminar regime. Just let me correct the spelling error. Right. So it is flow through capillary. Only thing we do is a gravity flow, because we wanted to do it in the laboratory. We just fill the you take a cylinder or take a chamber, beaker. Let's just draw that. This is you are going to do these experiments, right? So there is a chamber, beaker if you like, and at the bottom of the beaker, either in this direction, there is a small capillary. The reason for small diameter, reason for capillary is that the diameter is small. Therefore, Reynolds number in this capillary would be definitely laminar. And then if you have this liquid, you can measure the time required for liquid to drain, or you can measure the flow rate, and the flow rate you can calculate. From the flow rate you can calculate the strain rate gamma, and from the head applied you can calculate tau w, and then you can calculate the flow rate at different heights, or just measure how height changes with respect to time, and you can calculate what kind of behavior do you have between tau w and n. Okay, there is another kind of viscometer, cone and plate kind of viscometer. So here is a cone and plate. So what you have is a plate, and there is a cone. This is the cone. Small gap is created between them, and the gap between the cone and the plate, we take the fluid of which we want to measure the viscosity. Let me just draw that for you. Yeah, we fill this gap with a fluid whose viscosity we want to measure. So this gap is very thin, so it behaves like a cuvette flow. This cone is rotating, and we measure the stress or the force required to keep this bottom plate stationary. It is like a shear flow now. It is like a cuvette flow. Gap is small. See? Or you could have a falling cylinder viscometer. Falling cylinder means you take this tube, fill it with a liquid whose viscosity you want to measure, take this solid cylinder and allow that solid cylinder to drop inside this liquid. Solid cylinder will settle. Gravity force minus buoyancy force, drag force. So gravity force minus buoyancy force equals drag force. Cylinder will descend at the terminal settling velocity, and if you do that, this is like a cuvette flow. This is, I have one wall, I have this wall which is moving downwards, I have a stationary wall, cuvette flow. Okay, and the gap between the cylinder, inner cylinder which is falling, and the outer vessel wall cylinder, there is a liquid here. This is the same liquid that is here, right? Same liquid. So now it is like a flow between two parallel plates if the gap is very small, and then you can relate the shear rate. It is like this situation. It is like this situation, as if this is the wall of the inner cylinder which is falling, going downwards, and this is a stationary wall, and then you can calculate the gradient strain. We have seen this cuvette flow, we have seen. That's why we saw cuvette flow, because we wanted to do viscometers here. All these viscometers are based on the principle of cuvette flow. Small gap, allow one layer to one wall to move, measure the force, measure the rotation, or measure the velocity, which is a measure of the strain gamma, and then you can calculate the viscosity. Okay. So if your apparent viscosity and the shear rate, if this is the kind of behavior, typical behavior. So this is like a cross model. You see, this is like a zero shear viscosity. Let's take another color. This is like the zero shear viscosity. Shear is very small, mu 0, and this is like the infinite shear viscosity, mu infinity. Right? You see this kind of behavior. So cone and plate viscometer work very nicely in this shear rate regime. So this is 10 raised to 0 means 1. This is 100, 10 raised to 200. This is 10. This is 100. This is 1000. So approximately between 1 to 1000, the cone and plate viscometer works nicely. If you want to go to very low values of strain, you can use Brookfield viscometer, the two cylinders rotating, either cylinder rotating or outer cylinder rotating, or sometimes instead of cylinder there is a disc that is rotating. And if you want to talk about high shear rates, if you want to make measurements in high shear rates, you can go to capillaries, capillary viscometer. Remember, pipe, we had a strain rate of 240 something. Now as you reduce the diameter, now my strain rate is going to be higher and higher. So you can see that capillary viscometers operate really in this regime, 1000 plus of strain rate. Okay. So at an appropriate position of the shear rate for which you are interested in measuring the apparent viscosity, you can select a type of viscometer that is most suited for your range of viscosity measurement. Okay. One last small part, something called as Rabinovich equation. Okay. So remember, we had talked about flow rate. So flow rate was Q is equal to Vz multiplied by area perpendicular to the Z direction. That was R delta theta. R delta theta is 2 pi R, and dr integrated from 0 to R. Now I can integrate this by parts, right? So you remember integral of uv, integral uv, something that we did in say 11th standard, is u integral v dx minus, that's this minus sign from integral du dx integral v dx, right? Remember that formula? Okay. So integrate this r, you will get r square by 2, that will go away with this 2, or 2r you will get integrate, you will get r square, and v differentiation you will get dvz by dr, and dvz by dr is nothing but gamma. Okay. And then r we can write using tau w and tau. So r is nothing but r tau rz by tau w. If you substitute this and you substitute this, you get an equation in terms of flow rate, that is in terms of now tau w. The limits of integration are now 0 to tau w, and gamma tau rz square d tau rz. Now depending on what stress strain relationship you have, we substitute that relationship here, whether it's a Bingham plastic, whether it is a pseudoplastic shear thinning, whether it's a dilatant shear thickening. We can substitute that here and get an expression for flow rate. So experimentally, when we measure the flow rate, we can back calculate the stress strain behavior which best fits this equation. That's called as a Rabinovich equation. So right now you don't have to do all these things nowadays, because viscometers are there which allow you to directly measure the viscosity based on cuvette flow principles. So you don't have to really do this, but olden days when people had only flow through pipe, they used flow rates as a measure of what is the as a measure of the deformation, and then back calculated the rheology based on that. So material that we have done in this lecture, they are from Transport Phenomena, Bird, Stewart, Lightfoot, BSL in short. all the material that we did so far is in chapter 8, sections 8.1 to 8.3, and you can solve these problems for homework. 2b.6, 3.63, 3a.1, 3.64. Some of them are solved problems, some of them are unsolved problems. They are based on these viscometers. See, it's based on cone and plate, it is based on this falling cylinder, and so on and so forth. Okay, so solve these problems, make sure that you have understood this well before you go forward. So what we have done so far is now completed the microscopic balances part. That subtopic now we have completed. We have looked at laminar flow, we have derived equations of motion, continuity, Navier-Stokes equation, we have solved them for simplified problems, and we have used seen non-Newtonian flow behavior as well, and how do we account for that non-Newtonian flow behavior, and more importantly, how do I measure viscosity, whether it is dynamic viscosity for a Newtonian fluid constant, or whether it is an apparent viscosity, it is changing with respect to the strain rate. How do we make all those measurements? So that's what we saw in this class. So the microscopic part is complete. The next part, of course, now is looking at turbulent flows very, very briefly. So that's going to come in the next lecture.